Hello everyone, welcome back to the second video for Math 9 ASI. Today we're going to be going over a little bit more over limits, and we're going to be looking at the definition of the derivative. So let's go ahead. So first off, we have limits that do not exist, and there's three different cases that this can be. Either we're approaching different values from the left and the right, we increase or decrease infinitely, meaning that we're either approaching infinity or negative infinity, or the function is oscillating even if we zoom infinitely close. So it's kind of weird. You might think oscillating like sine of x, but that's actually fine. This is only when we zoom super close and we're still oscillating. I'll try to show that when we get there. So this is our example for case 1. This is kind of similar to what we were looking at last week, but here we have f of x where it's x as x is less than 1, and negative x plus 3 if x is greater than or equal to 1. So that's what this graph looks like. And we're looking at the limit as x approaches 1. So we can see if from the left, it looks like we're approaching 1, but from the right, it looks like we're approaching 2. So here we just say the limit does not exist. Our second case, our example here would be f of x equals 1 over x. So this could also be a case of case 1, but either way, it's still not going to be the same. From the right, or from the left here, sorry, we're approaching negative infinity. We're just going to keep going down infinitely. And from the right, we're approaching positive infinity. We're going to keep going up. This is still the case if it's like 1 over absolute value of x, where both of them are going up. We just can't be approaching infinity for our purposes right now. And lastly, for case 3, this one's not going to be nearly as common as the other cases, but it's still good to know. So in this case, we have f of x is equal to cosine 1 over x. And we see here, this is what the graph looks like. It's kind of gross. We can just see a lot going on. And if we zoom in, we see that we're just going to keep oscillating up and down, never really settling on a point. If you want to play around with this, I'm using Desmos for these pictures. I think it's really interesting to see this one in particular. So tangent lines. So tangent line can be thought of as a line parallel to the slope on a graph at a specific point. So it's kind of hard to think about right away, but if we're looking at, for example, f of x equals x squared, we want to look at, say, the point x equals 1, and we have this line that's in green. This is describing the tangent line to x squared at x equals 1. You can see we're kind of going by, and we only touch the graph right here, and then we continue onwards like that. So it's just, most of the time, it's only going to be hitting the graph at one point. It's just going to go right up parallel to where it is at that exact point, and it's going to continue on. So how can we find this? Well, we want to be able to find the slope of the tangent line. And we can call this has a name, it's called a derivative. And the way we can find it is we can use two things that we were going over last video, secant lines and limits. So right here is the definition. I think it's pretty useful to know. So I think to better show this off, I'm going to go over the example we had. Okay, so I'm going to be trying something new here using this whiteboard. So our function is f of x is equal to x squared. And we're going to be using the definition of the secant line here. So if you recall, we have f of b minus f of a is over b minus a. And here, our b is just going to be x plus h. So some point x plus some other value h that's shifting us. And our a is just going to be x. So we can go ahead and rewrite this as f of x plus h minus f of x over x plus h minus x. And here we see we get a cancellation, so we can cancel the x's. And we're just left with f of x plus h, minus f of x. And that's going to be over h. And now to finish off our derivative, so in this case, like I mentioned before, we're only going to be passing through the graph at 1 point. So we can only really use 1 point. So to emulate this, we're going to have the h is going to be, we're going to be taking the limit as h approaches 0. So let's go ahead and write that right there. And this is going to be what our f prime of x, or the derivative of x, is going to be equal to. So we can just go ahead and plug in and solve this. So plugging in, we have the limit as h approaches 0. Plug in x plus h for our x. We have x plus h squared minus, this is just going to be x squared, right? Ooh, sorry. And we're going to have h on the bottom, right? And we can go ahead and simplify this. So continuing, we have limit as h approaches 0 of, if we FOIL out what we have before, we have x squared plus 2hx plus h squared minus x squared is from our f of x, and that's all going to be over h. So if you notice, we can cancel the x squared minus x squared. And we can also pull out this h here. So rewriting, we have h times 2x plus h over h. And now we have our h's cancel here. And we're left with limit as h approaches 0 of 2x plus h. And now, since plugging in 0 isn't going to cause a 0 in the denominator, we're free to plug that in. So our limit is h approaches 0. So plug in 0 for h. And we're just going to be left with 2x, right? And what were you trying to find before? We wanted to find the equation for the tangent line at x equals 1. So if we plug in 1 here, 2 times 1 is 2. So the slope of our tangent line at x equals 1 of x squared is 2. So we want to find the equation for the line, right? So now what we can do is we have our point, which is 1, 1, and we have our slope. So we can just use point slope form. So I'm going to clear this again. And what we're going to do is we're going to use the form, hopefully you remember, this is y minus y1 equals slope times x minus x1. So here we have y minus 1 equals 2, which is what we just got, x minus 1. Let's rewrite this to be 2x minus 2, and moving the 1 over, we have plus 1. And we have 2x minus 1. So that's the equation for our tangent line at x equals 1. And real quick, let us look over at our slides. And you can see, yes, we can verify 2x minus 1 is what we were trying to get. That's the equation for the tangent line here. So if you have any questions, leave it down in the comments. I have another worksheet in the comments too, and feel free to come to my office hours. Those are going to be posted below. Thank you everyone for watching.